Hello and welcome to this presentation. I'm Mohammed Shazad and I will be presenting this paper titled Load Balancing and Routing Strategy in Fog Computing using DRL, that is Deep Reinforcement Learning. We have the problems to discuss that why we are doing this work. So first of all, we want to cope with the growth of IoT, and since the huge amount of data that is being generated by the sensors that the cloud cannot handle. So we need to transit to a new technology in order to meet the needs of real-time applications in terms of latency and how to build the resource management strategy to balance the system loads. Uh, for that, for those problems that I just mentioned, the solutions we are looking for is to optimize the fog system resources, use artificial intelligence with the objective to reduce the processing latency and reduce network latency. Uh, so this is what we really want to do, is to establish a load balancing strategy based on deep reinforcement learning technique, which is going to provide with a link state routing strategy for a fog cloud IoT environment. We propose a load balancing strategy based on a DRL model for a fog system. The objective of the strategy is to optimally distribute the generated workload among the computing entities in order to avoid the overload and underload condition of each one. So ultimately minimizing the processing delay. The proposed load balancing strategy here is improved with a link state routing protocol based on Dijkstra's algorithm to deal with communication latency, and the routing algorithm that aims to transmit the tasks to the selected nodes via least congested path in the network. So by reducing the communication delay, the load balancing and the routing strategies, they are implemented in load balancer smart controller, which is LBSC, which collects the required system information, including the nodes, link states, and selects the processing nodes using the DRL agent, and routes the task to the destination. So the proposed strategy is simulated and tested in a dynamic environment in which the workload generated from the IoT devices varies and it can reach a high rate. Uh, in DRL, an agent is used to interact with the environment and take action for each current state. The learning process of the reinforcement learning involves using a reward system in which the agent learns the appropriate action to take in a specific state based on received award. The main components of load balancer smart controller are highlighted here, that is responsible for distributing the tasks among the nodes and routing them to the destination. The smart controller is always kept updated in real time about the state of the environment by receiving the nodes and links state through the control interface. For each task received, the task management module sends a selection request to the AI manager submodule. Then it commands the selection module and the source node ID to the routing manager submodule that commands to the routing module. So using the node's state information, the DRL agent deployed in the selection module, it chooses the destination node and then it sends its ID to the routing module. And after that, the Dijkstra's algorithm implemented in the routing module uses the source and destination nodes ID to obtain all possible paths from the routes database. Then it chooses the most suitable one based on the link's state. So in order to route the task to the destination, the selected path is included in the task data using the packet constructor submodule and transmitted through the routing interface. So at first, the environment sends the state to the agent. The agent uh, either explores the environment or it exploits its knowledge. So at the beginning, the agent has no knowledge of its environment, so it will explore it by performing a random action. Then, as the action agent exploits more and more of its knowledge, the more it explores, the more it becomes increasingly greedy in terms of exploitation. So in all cases, the action taken by the agent that will be made by awarding the appropriate reward or penalty. The set state action, uh, uh, like the set state action and reward, that will be stored in a memory, which will be later used in training of the neural network. So if it is not the last state of the scenario, the process is repeated. And if it is the end of the scenario, we move to the learning part. So we take a sample from the memory to perform the training of the neural network. And if this is not the last scenario, we move to the next scenario by repeating the process. And uh, so we move to the next scenario by repeating the process. Otherwise, we save the neural network model and stop the process. So here, link state routing is uh, divided into three steps. First, we have a type of dynamic routing. So link state routing is a type of dynamic routing. It allows the automatic adoption of the routing strategy by exploiting the states of the links of the network. And then the link state routing it does the calculation of the optimal path based on Dijkstra's algorithm. Uh, as we can see here, the most optimal path is the one shown in red with an overall cost that equals to 60. The agent received by interaction with the environment the current loads of the nodes for each state of the nodes. Sorry, the agent receives by interaction with the environment the current loads of the nodes for each state of the simulation, and a node's load is quantified by the number of tasks in its queue. By exploiting this information, the agent will have to make a decision by choosing a node for the next processing. This decision will be later judged by the algorithm, and the agent receives a reward if the chosen node has a satisfactory load, means it meets the node needs of the IoT applications. So if it is not that case, the agent will not receive any award. So after several iterations, the agent will be able to establish the optimal strategy for load distribution between the nodes. Uh, the load will be distributed to the right nodes, and the agent should be able to route the tasks to the appropriate nodes, that is with less load, as shown in green paths, that the free path shown in blue. So we use a programming interface, uh, YFS, for the simulation of the system to develop with Python. Then we use a Cloud P2.x large instance on Amazon Web Services based on Tesla K80 graphics card to carry out the learning sessions. Uh, for the processing latency, we can clearly notice that our technique significantly minimizes the latency time compared to other strategies like random, round robin, and weighted RR. Regarding the latency of the network, we can see that the classic techniques, random, round robin, weighted RR, they increase with the increase of the nodes. On the other hand, our technique that gives stable latency where it does not exceed 9 milliseconds because it uses a routing link status. For the global latency, it is obvious that our technique presents the best times because the global latency is the sum of processing latency and the network. So it presents almost half of that of weighted RR. So now we reach the conclusion that the exponential deployment of the IoT that requires the fog computing systems and optimal load balancing that is essential to guarantee quality of service. Here in this work, we proposed a load balancing strategy that was based on DRL combined with Dijkstra's routing algorithm for a fog cloud IoT system. And the results they show the importance of routing for load balancing, and our solutions they are clearly more effective than the traditional strategies like round robin, weighted RR strategies. So the impact of artificial intelligence that's really important to optimize the performance of the emerging technologies. So this brings me to the conclusion of this presentation. Thank you very much for listening. Thanks. Have a good day.